so thank you again. Our speaker today is Dr. Connie Borror, who is a professor in the School of Mathematical and Natural Sciences. She received her PhD in Industrial Engineering from Arizona State University in 1998, and her research interests include design of experiments, statistical quality control, and measurement systems analysis. She has over 70 journal articles. She's co-authored 3 books and edited the 3rd edition of ASQ's Certified Quality Engineer Handbook. Dr. Borror is a past journal editor for Quality Engineering, a senior member of IIE, and a fellow of both ASA and ASQ. Today, Dr. Borror will be presenting on regression methods, discovering relationships among many variables. And this is a popular talk that covers a lot of basics, but a lot of times we need to brush up on these kind of things. All of the telephones and microphones have been muted other than mine and Connie's. So if anyone has any questions or comments during the webinar, please freely use the questions interface in the GoToMeeting control panel that you see on your screen. And I will hold all of these questions until the end of the presentation, at which time Connie will answer those for us. So at this time, I'm going to hand things over to you, Connie, and thank you again so much for presenting with us.
Thank you, Amy, and I hope everyone can hear me all right. In a few moments, I'm going to show you my screen and we'll get started. Yeah, the topic is going to be, well, let's see, wait a second. Sorry, hide control panel. Sorry, I forgot how to do that. I have a lot of fun with this topic, and it's regression methods discovering relationships among many variables. And it's such a wide and a varied topic that we could cover hundreds of things, and if we had all the time in the world to do it. But what I wanted to do today is just kind of a review and a kind of entry-level presentation on simple regression going into multiple regression, and some of the cautions that we need to be aware of or make sure that we keep in mind as we start using them more and more into these areas of the analytics, having lots of data to kind of mine through, that we want to make sure that we're using some of these techniques correctly. Now, I'm only going to talk about a very small area, but I hope it is a good refresher if you've seen this before. I found I think a somewhat interesting example that I'd never seen before that I wanted to present, and I hope you enjoy it. So what we're going to do is, my slide will go down, thank you, is the agendas. We're going to review very quickly simple linear regression, give an intro to the multiple linear regression, talk about significance testing, and along with that, cautions in the use of some of these tools and things that we need to be aware of as we walk through, and then give you a summary of what we've been talking about. So basically, just a reminder, regression analysis is, of course, a technique or a set of methods to determine relationships between 2 or more variables. And in general, there's 2 purposes, although we often find there are more. The 2 general purposes are making predictions out of some outcome of interest using some inputs, okay, as you'll see in just a moment, and be able to estimate what effect some inputs, those input variables, have on the outcome of interest. What are their relationships between each other? Can I get some relationship? Is there some relationship that I can use and try to make possibly some predictions, do some interpolation, some extrapolation beyond that? So just a very basic, what you see here is a basic scatter plot. I've got 2 variables. I'm just calling them right now X and Y. I'll show you an example in just a few seconds. So we got 2 variables. We have X and Y, and it looks like as X increases, Y increases. There appears to be some linear relationship between the 2, although it's not perfect, and we shouldn't expect it to be a perfectly straight line. or the data to fall along a straight line perfectly, because there's always that inherent variability that we can't do much about, or there may be something else going on that we might not have captured with just these two variables. So there are lots of situations out there, especially these days, where we want to try to fit an equation to this data so we can predict y, my response, my y variable, from some input, my variable x. Okay. Now, again, trying to fit a line through that, of course, we're not going to be able to fit a line that goes and connects every single point. The best we're going to be able to do is try to fit a straight line right now and try to hit or come as close to those points as we can, kind of on average. In other words, watch this next busy slide for a second. So we would like to fit that straight line that you see there. We find the equation of the line, which we know how to do. We've been doing that for a long time. That's y equals mx plus b. So we want to fit an equation of the line that best fits this data. That idea of what's the best fit, though, we want to have that line that represents the predicted value of y. That's what that line is. It's the predicted value of y for each value of x. So if I came up with an equation, y equals mx plus b, and I say, here's what x is, I can make a prediction on what y is. So the line represents all of my predicted values. The actual observations, the little dots you see there, are the real values at that value of x. So what you see for a particular value of x, if you look down at the x-axis, it looks like, around x equal 12. You see that there is a dot there, and you see where I say error pointed at it. And I have that dot, and then between that dot and straight up where I hit that line, that difference is what I call error, because the dot represents what really happened. What I predicted would happen at that value of x is my y, is on that line, is my y value. So that error is how far off I was from what the actual value was when I made my predictions. So this error is associated with every value of x. Okay, and it's the difference between the actual value, what really happened in y, and what I predicted would happen in y given x. Our goal is, as we said before, we can't fit a straight line through all of these data points. So how do we kind of get a line of best fit? And there are different ways to do that. One goal is to find the equation of line that will minimize these errors kind of an overall, like kind of minimize the errors if I could add them all up. What would be the minimum sum? That doesn't work exactly well, because honestly, the way that we're going to create that line, if we create it a certain way, if I find all those errors, as I talked about, actual minus the predicted for every observation, and I added up all those errors, those what we call when we actually do them residuals, it would equal 0. That's not very helpful. So one way to do this is to, well, instead of just adding up all the errors, how about we get the error or the residual, we square it, and then we add all of that up. Get the sum of the squared errors, and our goal being, let's find the line that will minimize that quantity. And that's what we do when we talk about creating a line using least squares criteria. Okay? So in general, that's what we want to try to do. So let's look at an example. This came from an article. I'll provide the reference. Do patients like good care? In this article, researchers conducted a study to determine if measures from Facebook, such as likes, where I think those of us who are on Facebook, we know exactly what that means. They wanted to know if a measure such as likes can be used as a proxy for patient satisfaction and hospital quality, which they measured as 30-day mortality rates and patient satisfaction. One relationship of interest then was the number of likes for a hospital on Facebook and 30-day mortality rates. Now, as we all know, 30-day mortality rates, we like those to be low. What we want to know is there a relationship, or can we predict the number of Facebook likes based on 30-day mortality rate? What you see on the right-hand side is just a small subset of a set of data that they provided. And each row represents a different hospital. And an asterisk represents that there is missing data for that particular observation. So we'd want to know, is there some kind of relationship between this? Can I make some predictions? Can I use likes as a proxy in place of, say, 30-day mortality? And to do that, I need to know if there's some relationship between these two. So let's look at, first thing we want to do is let's plot the data. So we plot the 30-day mortality rate versus the Facebook likes, the number of likes the hospital received. As you can see here, the scatter plot, I see that I have an observation that really doesn't kind of go along with the rest of them up there in that left-hand corner. And I bet later on, when I do a full analysis of this, although I don't get to do it here because I want to cover some different topics, what I would do is I'd look at that upper left-hand corner and say, that may be what we call an influential point. If we try to fit a straight line to this set of data, which we're going to look at and say what are the techniques or what's behind doing that, we would probably see a line that is going downward, showing a decrease as I move from left to right, and is probably going to be pulled towards that very unusual observation up there in the left-hand corner. So what we're going to be able to do is we're going to take this data. We see what it kind of looks like now. Might be a little bit of curvature. If that point wasn't there, what's really going on? Right now, let's look at what we would do if we just wanted to try to fit a simple linear relationship between 30-day mortality rate, my X, and Facebook likes. What we believe is, or their theory behind what they were writing about was, of course, the lower the mortality rate, the better the liking, or the more likes they would receive on Facebook. And I think you're kind of, hopefully you're already thinking about why that's not necessarily a good thing or the only thing to look at, because we know how Facebook likes can occur, or many people who are on Facebook understand that likes what your, I'm not sure why, sorry about that, hang on. That we want to know in this particular case, they may click like simply because they want to see or get information about your particular hospital, not because they actually like it. So we know there's a lot of variability in here. But let's use this data set to try to look at some of the techniques and methods that we'd use in linear regression. So regression analysis, we said, statistical net technique, we're used to fitting a straight line between one input and one output, y equals mx plus b. So okay, in statistics we might call it y equals b naught or b sub 0 plus b1 times x. Our goal is we want to use x to make predictions in y. Again, x is going to be called our independent variable, regressor, predictor, or input. Y is our dependent variable, our response, our output, our outcome, something that we think relies on the input variable. So in theory, remember when we look back at that first set of data and it was kind of all over the place and we couldn't fit a straight line through it, in theory it would be great if we could. And we would fit, say, if we could fit a line through or fit all of those data points, we would have a line like y equals the intercept plus the slope times our input variable, but now there's plus some error. We talked about the error, so we're off by so much, but if that's in theory, we can't fit that exactly. So our goal is to find a regression line or a fitted line that fits this data best. And so we would get a y hat, we'd find out what's b naught, we'd find out what's b1, and we want to try to get that best fitting line. And remember, what I talked about was one way to get that best fitting line is using least squares. Finding or trying to minimize that error. Once we have actual data and we can calculate that, we know that these are called residuals. But what we want to be able to do is we want to have very small errors or residuals. We want our predicted value to be very close to the true value for any x. Again, we could use least squares criterion. We could fit what we call a regression line or regression equation. And we want to make those errors as small as possible. So here's our data again, small set of data, and let's see what this would look like if we wanted to fit a regression line. If I use least squares regression, in this problem, x, my independent variable, in this case is 30-day mortality rate. It's independent. We hope the hospital has some control over it, but it's what our input, it's what we think is having some effect on the number of likes or we want to see if it has an effect on the number of likes that we get on Facebook, where our dependent variable in that case is Facebook likes. Okay. So if we fit a regression line using standard software package using least squares criterion, our fitted line is y hat equals, wow, 1,934 minus 99.1 times x. We can use this line to make predictions. Or what we should think about is Facebook likes a good quality indicator proxy for 30-day mortality, meaning that do I see such a relationship between these two such that if the Facebook likes is low, or excuse me, if my Facebook likes are high, then that must mean, oh, my mortality rates are low. We can understand some of the difficulty in that type of interpretation, but that's what we're looking at. What if we want to predict Facebook likes if the 30-day mortality rate is, say, 16 for that month? So we would plug 16 in for x, and we get we would predict the number of Facebook likes to be 348.1. However, we still need to run some tests to see if this line is significant. I can take any set of data, any x, any y, I can fit a line to it. Just because you can fit a regression line or fit an equation to a set of data doesn't mean you should. And I think that was indicated a little bit when we looked at the scatter plot of this particular set of data. Okay? So what we need to be able to do is we need to be able to test. I want to be able to test to see if my regression equation is significant. Is x a significant regressor for y? Is 30-day mortality rate a significant regressor for Facebook likes? We could do that using ANOVA, testing for the significance of regression. And we also can conduct tests on individual regression coefficients, the t-tests. And in both of those cases, what we're testing is that the slope, the coefficient on x, our independent variable, is 0. And for simple linear regression with only one input, the ANOVA test and the t-test are going to tell us the same thing. So in essence, why do we test beta 1 equals 0? Why is that something that's significant for us, for both of our null hypotheses? Such that if I reject that null hypothesis using my data, if I get a p-value that's small, if I reject that null, how does that tell me, or why does that tell me that my regression line is significant, that my x variable belongs in the equation with y? So, well, let's think about it. What happens if we don't reject it? If beta 1 is equal to 0, let's say that I cannot reject the null hypothesis. That means that beta 1 is basically 0 or very close to it. So let's say that we can't reject it, so the coefficient on x is 0. That takes our original model from beta naught plus beta 1x plus epsilon down to y equals beta naught plus epsilon. Beta naught's just a constant. That means for any value of x, I'm always going to get the same value of y in my predicted value if I don't have my error. This indicates there's no statistically significant relationship, linear relationship between x and y. And that's why we want to test it. If I can reject it, then I can say x belongs in an equation with y. But again, as you're going to see, that doesn't necessarily mean that I now have a great equation that I see that the relationship between x and y, or 30-day mortality rate and Facebook likes, is significant. Let's run with it. Let's just use Facebook likes. Oh, look, Facebook likes are really high. Wow, mortality rate must be really low. People are really liking us, and so forth. How can we use those as indicators? A little iffy. So in the ANOVA test, in simple linear regression, we have one regressor, and what we're doing is we're testing that at least one of the regressive variables belongs in the model with the response. Again, we only have one x variable, so we only are testing our particular variable x. So our null hypothesis is that beta 1 equals 0 against the alternative that it's not. The t-test on individual regression coefficients, we can test the intercept and we can test the regressor coefficient. Whether you use ANOVA or the t-test, the interpretation is the same. If the p-value is small, we reject the null hypothesis. And again, rejecting beta 1 equals 0 says the coefficient on the regressor is non-zero, and that the regressor belongs in the model with y. Okay? So here are the results from a computer software output. Here are the t-tests at the top and our ANOVA at the bottom. The ANOVA at the bottom, let's start there. I like to start with the ANOVA. The ANOVA tells us the p-value is very small. I can reject the null hypothesis. That means that my variable, which is 30-day mortality rate, is a significant regressor, or it belongs in the model with our response y. Our t-tests at the top show both p-values are very small. What we see is that both the constant, the intercept, and the coefficient or the slope are both non-zero, and we can fit a model using both the constant and our slope and our regressor variable. Since they're small, they both belong in the model. Based on the ANOVA, we see the regression model is statistically significant. The regressor belongs in the regression model with the response. Here is the model again that we fit, and this where x again is our 30-day mortality rate. But again, is the model adequate to predict quality? Remember, we wanted to see if Facebook likes could be used as a proxy for some of the quality indicators that they're looking at. How else can we determine that? I've just shown, and this can be sometimes be a problem, is that some people just show, here's my t-test, here's my ANOVA. They say everything's okay, so here's my model, I'm going to use it. But of course, there are several other things we need to be able to do. You have to do your residual analysis. We have to test with a model adequacy. We should look at other metrics as well. What about the correlation between x and y? What about the coefficient of determination, or R-squared, for this set of data, for involving x and y? So let's look through the first two at least and see what's going on. So the ANOVA table for any simple linear regression model, if you recall, looks like this, where we have that sum of squares column telling us something about the variability. We have a total sum of squares, total variability in our response. We have regression sum of squares, the variability due to the line that we have fit that involves, in this case, 30-day mortality rate. And then you have the error sum of squares. I like to call that kind of the garbage can, the variability that I don't know what it's due to yet. Cannot be explained by the line I fit, and I don't know what else to do with it, and I don't know what else it might be due to. So that's kind of our error, our inherent variability right now, until maybe we know of other regressors we could put in. But right now, it's just our error. So the coefficient of determination is just one metric, one of many that we could look at and see, well, what does that tell me? Well, R-squared, this coefficient of determination, is found by the regression sum of squares over the total sum of squares. And the regression sum of squares, this thing should be high. We want this thing as close to 1 or 100%, because it tells us the amount of the total variability that can be explained, that we see in our response, that can be explained by our line that we fit. Now, that's really interesting, because this tells us, what kind of control we have over that variability in the response. Okay, and the 1 minus this, if we use it in decimal for 1 minus this R-squared value, or 100% minus that, and if it's in percent, tells us how much of the variability is left over in the trash can that that's due to, well, I don't know what that is, and I have no control over it. So you want most of this variability to be able to be explained by the regression line you fit. Well, here's where we start to kind of fall apart, and kind of with this set of data, is that the R-squared value for this is 0.143. That means for our 30-day mortality rate and Facebook likes, only about 14% of the total variability that you see in the number of likes across those hospitals can be explained by the regression line we fit that involved 30-day mortality rate. So in other words, what is that? 100% minus that, or 1 minus that, gives us about, just about 86%. 86% of the variability that we see in the Facebook likes, I don't know what it's due to. I don't know where it's coming from. I have no control over that. So this is one of the, besides the plot we saw, one of the first indications that even though it was significant in the regression line, that doesn't necessarily mean that the line I fit is going to be good for indicating quality that I'm interested in. Correlation coefficient's another metric we can look at, but sometimes what people want to do, and I always encourage this, do a lot of graphics of your data when you get it. Do some summary things. Some people like to do, when they've got want to do some regression analysis with just one input or one regressor and one response, is calculate the correlation coefficient to help them decide if they should even move on into some further tests. And I think that's fine to calculate it beforehand, but oftentimes I don't recommend it being the guiding light as to whether or not you should continue on, and here's why. First of all, the correlation coefficient measures the strength of the linear relationship between the two variables. So you know it's a number between -1 and 1. The closer this number is to -1 or 1, the stronger the linear relationship. Again, if your slope, like what we have, the slope, the sign on the slope that we have for our regression equation is negative. So R, when we calculate the correlation between 30-day mortality and Facebook likes, should also be negative. Again, if R is close to 0, there's no linear relationship between the two variables. For our problem with just the Facebook likes and 30-day mortality, the correlation coefficient is negative 0.378. That falls into that gray area that some people will say that's mildly or moderately significant. Others would say that is not. This appears to be moderately significant, and I would look at that as just one more metric that it's not very high, it's not that strong. That's not reassuring me that 30-day mortality is the only and good indicator for Facebook likes, or that Facebook likes, in other words, could be a good proxy for 30-day mortality rate. Okay? So we've talked for the first half hour here, 27 minutes, about simple linear regression and reviewing that and going through the kind of the nuts and bolts behind it with just one variable. Let's move into what happens in multiple regression. Now, we had the simple linear regression, which is just one input, one output, one regressor, one response. In multiple regression, we're still looking at one response, but we may have more than one input or more than one regressive variable. We might try to fit the model that you see at the bottom of the screen there. Again, it's just like our simple linear regression, except now I've got more than one input that I want to try to model at the same time. Very common situation nowadays because of the plethora of data that we get that's collected automatically, and data that we're trying to capture from different sources. So I'd like to be able to fit a regression model that you see at the bottom. So in our example, we're going to add a couple of more variables. Let's say I add one more variable, and that is the variable days active. Now what that meant from the authors of this paper, days active meant how many days that this hospital had a Facebook page. Okay? So let's say that that is because the length of time could have an effect, and we want to be able to model and later on maybe more appropriately weigh the number of likes that we have based on that. But right now, let's consider this as an input variable. So simple linear regression would be just like we did, where our response is the number of likes, and our X variable, our input variable, was the 30-day mortality rate. In multiple regression, now it would be, of course, likes is the same response. X1 is now the Facebook is 30-day mortality again, but now we've added another variable, X2, that is the number of days active. So now I want to fit a model that looks, that would look something like you see at the top there, y equals beta naught plus beta 1 X1, beta 2 X2, plus some error term. If I fit that, then I put my y hat on there, and I've got my estimates for beta naught, beta 1, beta 2. Okay, so that's what the multiple regression. Now, the authors of this paper actually looked at several different input variables. So I have 4 of them here, and again, this is the same article. I'm going to see if they can determine if Facebook likes can be used as proxies. Now, we've already seen that they used the other quality metric that they wanted to try to relate to Facebook likes was the percent of patients that would recommend the hospital. You would hope that there'd be a strong positive linear relationship between that, between percent patient recommends hospital and the Facebook likes. But they also had another one, and they had two more on there, but I didn't add them in this particular example. But there was also a variable that was called community can post. And community, what we call community posts, were identified as those posts that were initiated by Facebook users rather than responses to administrators' posts. So on Facebook, if they liked the page, then they could go in and post something. And without having the administrators of the Facebook page or have, like, you know, started a conversation or discussion with a question or a comment, and then people will post their response to that. This says for that particular hospital that you can just go in and post things yourself. It doesn't have to be in a response to somebody that, or an administrator, to something an administrator put up there. So you can see this is a categorical variable, as either it's a no or a yes. We want to see if that has any effect on the number of likes that we have. Again, we have some missing data in there that we had to take care of. So now I've got 4 variables. It's 30-day mortality rate again. Now we have percent patients who would recommend the hospital, number of days the Facebook page has been active, and whether or not the Facebook community can post their own things without having an administrator post something first. So our model or equation of interest now would be what you see at the bottom. We want to try to fit an equation or a regression model that would fit those 4 variables. And this is what we mean by a multiple linear regression model in 4 variables. Okay. In general, if you had K regressors, we could do this for 7, 8, 9. I believe they ended up with about 7 in their actual study. In general, the model would look like this. Or you might have interaction effects, which we didn't look at, or I didn't look at in this case. We could also look at an interaction effect between 2 variables, and we could still get a multiple linear regression model. Okay. So in this case, again, here's our model of interest. If we fit it using least squares regression again, I'm going to use some computer software to do it and just show you the results. We want to fit the equation at the bottom, at the bottom there, y hat equals and what you see. In general, when you're building the multiple regression model, what you're looking for is this: a model that will give us the best possible predictions, or maybe explain most of the variability we see in the response. Now that model that we end up with may contain only some of the original independent variables. And one way of looking at this and trying to figure out what we want to be able to have is we want a model with as few input variables or independent variables as possible, but still give us good predictions and explain a lot of the variability in the response. One thing that I catch sometimes in reading articles of in several different locations is they'll give a model, an equation, they've run the least squares, they've done everything they were supposed to do, and they give the full model. They say all the variables that we had included in the study, here's the equation with all those variables. They'll give an R-squared, and they'll go on and make predictions with just that. I've seen that happen. And then I'll go looking for discussion of, well, what was your t-test, what was your ANOVA? Or they'll give us the ANOVA, which the ANOVA would say, yes, at least one of these regressors is significant. But I see no t-test, I see nothing else that tells me, well, what is the significance of each of the individual regressor variables? And that's important because if I see a model that has all of the regressors, there's lots of inputs, and all of them are in the model, and they're using that to make predictions, it kind of frightens me a little bit. I want to make sure that all of those variables that are in there, if they're not in there because someone said I had to have them in there, which has been done before, but if I'm basing my model on what is statistically significant, I'm not always convinced that every variable is going to be significant. So we should be doing some tests on that. So, for example, if we were to fit the entire model, my 4 input variables, here's what you'd see. Here's my fitted regression line using least squares regression. Okay? you can see the relationships. X1, remember X1 was 30-day mortality rate. I expected to be a negative sign on that because as that number increases, they would expect the Facebook likes to decrease. Although, again, we've got to be careful. It's not the only thing that's going on there. We have a positive relationship between the X2, which is the percent patients who'd recommend the hospital, and the Facebook likes. We have a positive relationship between the number of days the page was active, again, not surprising. And whether or not the Facebook community can post, you can see there's a negative relationship between that, depending on what we called no they can't as 0 or 1. But is this, without getting into those details right now, is this a good model for predicting Facebook likes? That is there a significant relationship between the input and the response? Each of the inputs, the independent variables, and the response. If someone were to just give me that equation and say, here, go use that to make predictions in these likes, and this should be a good model for, quality metrics for the hospital, I'd be a little bit afraid because no one's tested that yet. I just see how I can fit it right now. So the next step is to determine if they're statistically significant. We always want to do a thorough residual analysis to determine model adequacy. And if things are a little kind of hectic, which they often are with real data, where it's kind of messy, I want to talk a little bit more about the model building and the model fitting in these last few minutes that we have here. So just as in simple linear regression, we want to test for the significance of regression using ANOVA. But now the hypothesis is that the coefficients on all of the regressors, all of my X variables, is 0, that none of them are important regressors. Remember, for simple linear regression, I just had beta 1 equals 0. That's because I only had one X, one input. Now I've got several. Okay. If I reject that in favor of the alternative, the only thing I can say is, well, at least one of my regressor variables is significant, statistically significant, and belongs in the model with my response. But it doesn't tell me which one or which ones. Okay. You do an ANOVA table. You have an ANOVA. It would tell us reject or do not reject the null hypothesis. Okay. And again, what I have at the bottom there is very important. Even if you can reject the null in favor of the alternative, all it tells you is that at least one of the variables is significant. It doesn't tell you which ones. You need to do maybe the individual t-test to determine that. In our case, our ANOVA, if you look at our p-value, p-value is 0.013. This was fitting all 4 of our regressors. Based on the ANOVA table and our p-value, we'd reject the null hypothesis and conclude at least one of the independent variables, x1 through x4, is significant in the regression of Facebook likes. Question is, which ones? We don't know. ANOVA is like that person that you're in the cubicle next to you who runs in and tells you, I was able to reject the null, and then runs away and tells you nothing else about the problem. Doesn't tell you, what does that mean? Or he says, I can reject the null, and at least one of those variables is significant, and then runs away and doesn't tell you anything else. Those are very annoying. So we look at t-tests as one possibility. So we would test each individual coefficient using the t-test and p-values. Again, we'd reject the null hypothesis that particular variable, that particular regressive variable is not significant, that his coefficient is 0. If I can reject that in favor of the alternative, then it says that that particular regressor has a significant linear relationship with the response. Okay? We're going to come back to that because this is important. So here are my t-tests, my 4 variables. You can see the p-value for the constant or the intercept, 30-day mortality rate, days active, patient recommended, community post, all of these things. So based on this t-test, only days active appears to be statistically significant. Okay, so what do we do? Well, now we go back into the software and we take out all of the variables. We run the analysis by removing all the other variables that are not significant and refit the model. The p-value for the intercept is quite large as well and indicates that maybe the intercept is not significant. If that happens, it's up to the practitioner. It's very important for the practitioner to decide whether leaving the intercept in or not is important. And that may have to do with just the physical laws of the relationships between the variables. I'm going to leave it in and rerun the analysis and, oh, okay, wait a second. Now days active, let's see, 0.02. Now it's 0.234. Now it's not even significant at all. And all I did was remove, as I have been taught to do, remove the variables that were not statistically significant. Okay, so what happened here? Well, this is the downfall of, or I hate to say downfall, but this is the drawback of relying on just t-tests in multiple regression when we don't have this type of orthogonality that we like to have in, say, design experiments. What we need to understand, and I didn't allude to it earlier because I wanted to make it a big point here, is that the p-value for each regressor variable that you see tells you how important that regressive variable is in the model, given that all the other regressive variables are already there in the model. Think value added. If a regressive variable is in the model, if you've got all these regressive variables in the model, how important is this next one that you're going to put in? So these p-values, they're all conditional. So suppose two regressive variables, x1, x2, maybe they have some correlation with each other, but they're also correlated with the response. Then what that's telling me, what that says is that, well, I probably am going to find that their p-values are not, will show that they're not statistically significant given the situation. So it says this, if x1 and x2 are kind of doing the same thing and have maybe about the same effect or same relationship with y, okay, what good or what value is it for me to add x2 to the model if x1 is already in the model and explaining most of the or some of the variability or most of the variability in y? So when we look back at these coefficients, or these p-values, that p-value, say for example 0.396 for 30-day mortality rate, that says that's how important 30-day mortality rate is in explaining our response, given the other three factors are already in there. Percent patient recommended hospital, same thing. That shows you how important, which that p-value, it says is very high. That means he's not important. That says that percent patient recommends is not adding value. It's not adding any more to help explain the variability in the response, given that the other three factors or variables are already in there. He doesn't add any value. And that's the condition here. And that's one of the drawbacks to t-tests in multiple regression, when the variables are data that we've collected from either some process, some historical data, something we didn't control and couldn't manipulate like in a DOE. So that's how these t-tests can mask each other. Maybe I've got two variables in here that are really important, but they're canceling each other out. If, say, 30-day mortality rate and percent patient recommendation, if there's a correlation between those two, if they're doing about the same thing, their p-values are showing they're both insignificant, when in reality they may both be significant, but they're masking each other. One of them saying, here's how important you are given I'm already here. You don't add value, so you're not important. And the same thing for the other variables. So what do you do? And this is one thing I always recommend is do not rely solely on t-tests to try to identify what your important variables are. So how about trying some of the stepwise procedures that you could use to kind of identify or play with different, take variables out, put them in, that type of thing, or what's called best subsets. Now I'll leave it to you to look this up a little bit, but basically looking at algorithms of things that you might be thinking of doing anyway. So for example, back over here at the t-tests, some people might say, well, okay, because Dr. Borror or Connie said that we shouldn't really rely on these as is, I might want to take some out. So how about if I go back into the software, I'll remove 30-day mortality rate, rerun the analysis with those three factors left, see what I get. And then I'll do it again, I'll put 30-day back in, take percent patient out, do it all over again, blah, blah, blah. Okay, fine. you want to keep doing that, and doing that is when you have 5, 6, or 7 variables, I think I'd rather rely on other methods to do that for me, and that's what the stepwise procedures help me do. Again, I don't rely on any one of these. I rely on several different methods of, that are already algorithms that are already there to try to give me ideas of what factors or what variables may be important for me to get ideas of different models I might try and try to fit and see which ones are the best. I would examine metrics such as malloc sub p, the AIC criteria, mean square error, along with the R-squared and adjusted R-squared that we're going to look at. Knowledge of the system can be helpful, but not always. Okay, so instead of just relying on those t-tests, how about a procedure that will kind of go in and do what I mentioned? Put a variable in, take them out, put 2 more in, take them out, but do it in a systematic way that I don't have to do it by hand, thankfully. So here is the result. I ran just a simple stepwise procedure on the same set of data with the 4 variables. And what happened was this. When I ran the stepwise procedure, when variables could be added in, taken out, and compared and recompared, what it found was to look at not only days active, it did turn out to be statistically significant. Notice the p-value for that was 0.01. But also percent patient recommendation that would recommend the hospital. It was statistically significant as well based on this procedure. So what I would do is I wouldn't stop here. I would go back into my regular regression techniques, take these 2 variables and rerun my regression analysis with just these 2 variables and look at my statistics again. Look at my p-values from the t-tests again. Look at my ANOVA. Look at R-squared. Look at your mean square error, and then also, you want to look at something like adjusted R-squared. Okay, if we look at our t-test now, just using those 2 variables, I might have come up with this myself if I just played around, like I said earlier, take one out, put one back in. But it was easier to have let the software do it. But understanding what's going on is important. It says to use the model you see at the bottom. Okay, that our variables are both statistically significant, and here is our predictor variable, is our prediction equation. Is it a good equation? Let's still look. Remember the last one we had with 30-day mortality rate, which by the way didn't come out to be significant here. 30-day mortality rate, it was like 14%. Well, for the model that we have now, the 2-variable model, it's gone up to it has 31.8%. When I had all 4 variables in there, R-squared was 33.5%. With just my 2 significant variables, the R-squared is 31.8%. However, be very careful, and this is the second caution here. Be very careful with multiple regression because R-squared can be misleading. Now, I know I may be preaching to the choir, but I still see journal articles in different fields where people report an R-square from a multiple regression model they fit, and because that R-squared is so high, they think that they'll say that this model is significant and this is important, it's good, it's explaining a lot of the variability. It does not necessarily mean that the variables that are in the model are all significant, are all important in explaining the response. Because just by adding more independent variables, we can increase R-squared, even if those variables are not significant. And here's an example. I entered a 5th variable to our first model when all 4 variables were fit. I fit another variable in there, and I'll tell you what it was in just a moment. And my R-squared increased to just a little bit, but it increased to 35% from 33%. So I was able to make it go up by 2%. Still not very good. This is not a very good model for predicting the Facebook likes because a lot of that variable is left over. Some of it's just I can't explain. A better metric than, if we're going to look at explained variability, is the adjusted R-squared, which is an equation. Didn't really expect us to go through it, but it's a variable that takes into account how many degrees of freedom are going to be eaten up by putting in more variables. For our first model with all 4 variables included, the adjusted R-squared was 24.6. With just the 2 variables in there, the adjusted R-squared was 27.5. So now I have fewer variables but a better R-squared value, adjusted R-squared value. Still a caution here. the measures still indicate a poor fitting model, or at least one that can be improved. Because even with all these metrics I have here, even the highest one, say 33%, that still means more than 67% of the variability in the response, I don't know what it's due to. I have no control over. It's that error with the inherent that I don't know where it's coming from. It's difficult to make predictions if that much variability is uncontrollable and we don't know where it can't be accounted for. So even with what we've done, these are methods that we looked at, we still have a poor model here. Even though we have now significant factors, the metrics are telling me this is not a good plot. And if I were to look at the residual analysis, I'd probably see lots of problems in there. But I don't have that with for this presentation because of time limitations. So why is the adjusted R-squared a better measure than R-squared? Because the adjusted R-squared is calculated so that it will penalize you if you add more to the model, more independent variables to the model, and they're not significant. So here's my answer to my what do you know what my fifth variable was. Remember I said I added a fifth variable and the R-squared value went up from 33 to 35%. That fifth variable I entered were the ages of my pets that I've had during my lifetime. My cats, my dogs, my birds, my fish, my hamster. Their ages when they passed away over my lifetime. A variable that has nothing to do with the problem, yet R-squared went up anyway, simply because I added a new variable, which is why always be cautious in just relying on something like that when I'm doing multiple regression. So residual analysis, as I said, very important, even though we didn't have time to go over it here. We want to check all of our assumptions. And I'll tell you right now, if you look at this Facebook data, I think the best thing that's going to happen is we're going to have to do some type of transformation because our residuals analysis comes out to be a little bit off. So you'll have to still look at the model adequacy and examine the residual plots for each model. So I know I've gone through, some very high level, some things that at a different. But what I wanted to talk about was that these regression methods are very valuable tools. We've got to make sure that we're using them correctly and interpreting and using our knowledge of what's going on. So they're very good for identifying relationships and making predictions. We have to use caution. Cause and effect, which we didn't really talk about, but cause and effect cannot be determined simply by examining the historical data or using observational studies. We have to use designed experiments to still to uncover key input variables that may cause the change that we see in a response variable. Cause and effect cannot be identified from these methods. We can look at correlations and relationships. Watch out for influential observations. Even though we didn't cover it early on, you remember that very first plot with just the 30-day mortality and Facebook likes, there was that one point that stuck out there all by himself. When I did an influential analysis on this, we actually see that that value was very influential in what that line, the equation of the line, turned out to be. So we'd want to go back and say, well, if I can't throw that point out, what do? Do I use a weighted regression? Do I use some other type of method? So we've got to watch for that. And in this presentation, I've only given a small fraction of some material about regression methods, but I wanted to hit on the ideas behind really the caution and over-reliance on t-tests and metrics such as R-squared when we're working with data that comes from another source or that we haven't been able to collect ourselves or is not as a result of a designed experiment. So I hope this has been at least entertaining and maybe some food for thought, and hopefully we'll have a few moments for questions before we have to wrap it up. And if I can't answer your questions online, I can answer them via email. So thank you very much. I appreciate your time and your attendance.
Wow, that was a really good presentation. Thank you, Connie. A recording of the webinar will be available within a few days on the division's YouTube channel, and you can get to our YouTube channel by simply going to youtube.com and searching for ASQ Stats Division. ASQ Stats Division. So please remember to share this webinar with your coworkers, friends, family, colleagues, or anyone that you think might benefit from this topic. It's very informative. Also, I encourage you to check out the division's LinkedIn page, as well as our events calendar, which can be viewed at asq.org/statistics for the latest news on webinars, conferences, and many other topics. We did have several questions that rolled in throughout the presentation, so I'm just going to start with the ones that were closest to the beginning of the presentation, and we'll see how many we can get through.
Sure.
So,
and again, forward what you don't, we don't get to, and I'll make sure to answer them offline and provide the reference as well.
Okay, sure, sounds good. Okay, so the first question is, why should we do a T or a NOVA on the slope at all, as opposed to just going straight to the coefficient of determination?
That's a good question, and one reason is because the R-squared, the coefficient of determination, is not going to possibly give you all the information that you need in terms of what is a large R-squared, how large is large. Just like we have any problems with t-tests and interpreting how large is large for test statistics, we look at p-values for that. To see how big is big. R-squared, what's a large R-squared? Is 60%, 70%? You can use that, but I wouldn't use it as the only tool and go straight to that first. Even if it turns out to be very low. If you notice on this presentation, the R-squared was 14%. However, it said something about the variable 30-day mortality. It showed up to be statistically significant in the t-test and the ANOVA. So that very well could have been R-squared of 60%, and that would have happened. So I think it's all in the interpreting how large of an R-squared is large. And I think what the R-squared allows us to do is say, okay, 30-day mortality looks like it's important. R-squared tells me that it might be important, but it's not the only thing out there. I need to do more work. If you and I usually like to use the t-test and ANOVA so I can get an equation of the model and get my estimate for the mean square error that I can evaluate later on as well.
Okay, thank you. Someone else is asking, wouldn't we want to use the f-test and increment in R-squared as we add each successive predictor to the regression equation?
Yeah, you could use f-test and the partial f-test. You can do that. You could do a subset regression where we're doing, again, partial f-tests. You could do that as well. What's happening, what I showed here, is generally the approach that people that are just starting, that are often people that are starting out and looking at the results from the beginning, they'll go through this type of work in the software, and this is what they'll see. They'll start out with just basic regression, get t-tests and f-tests. But you're exactly right. I think as we go along, partial f-tests and subset regression, I think would be very important for that as well. And you could do that. You absolutely could. But that's not the first thing people often see when they try to use some of the software or are reading up about regression analysis. But that could be a whole webinar within itself, absolutely.
Okay, thank you. Maybe we have time for a couple more.
Okay.
Let's see. Nice overview. Let's see. For Y versus X, how do you deal with the correlation versus causation?
Oh, the only way we can deal with that is, first of all, we're not going to be able to tell cause and effect just from this historical data or this data that's been collected from different sources. And that's one of the drawbacks of any of the techniques that we use and in the analytics and so forth, that if we don't know how the data was collected, under what conditions, or if there's missing data, causation is not going to be able to be determined. What we can do is we can see if there's that correlation. If there's a strong correlation, that may be a good indication for me to say, all right, now that I see that if there's a strong relationship between this X and this Y, I see a strong correlation between them. can I design anything where I can control the situation or control the scenarios where I can collect data, the X data, or set the X data and collect my response from that so that it's more of a controlled condition, more of a designed experiment. So I like to use the information from the correlation results to say, where am I going to go next? Can I control for any purposes the input variables so that I could try to determine at least pseudo or in some ways some type of cause and effect between them. Otherwise, I'm not going to be able to. I'm just going to be able to say correlation, and then maybe someone's knowledge of the process, knowledge of the data itself can help me interpret and say just how strong they feel that this was one of the causes. But this is where we get problems with data that we read about or studies we read about where one year chocolate's good for us, the next year it's not. You know, it's again, situational where we have no control over the inputs and we're just hoping that it was collected in a certain way. But causation is only going to be able to be showed by designed experiments.
Okay, thank you. And
I hope that made sense.
Yeah, it made sense to me. Maybe we have time for just one more quick question, and then I'll send you the rest through email.
Okay.
Somebody's asking, what did you mean by just because you might be able to fit a regression line to the set of data doesn't mean you should?
Oh, good question. Again, that goes back to are the variables, do they make sense with each other? Does it make sense to try to make predictions from in Y, especially if you're making predictions from that input variable? A couple of things. You can fit a line maybe over a certain range, but what if that relationship changes over a certain range of X values? What if you go beyond those X values and you want to do extrapolation? How do you know that that relationship is going to stay the same and that you can actually still use them? The other thing is it nonsensical? For example, the example I like to give real quick here is there's a very strong linear relationship. There's a very high correlation between student or grade school children's shoe size, children ages 7 to 11, their shoe sizes, and their reading comprehension score on a reading comprehension test. There's a very strong positive linear relationship, almost perfect, like 0.9 something if you look at those two variables. But do I want to try to fit an equation between that to make a prediction? Do I want to try to predict what my kid's reading comprehension score is going to be based on what his shoe size is? You see what I mean? And same thing is that other way around. Why would I want to try to make predictions? And I wouldn't want to be able to say, well, if I can stretch my kid's feet and make them larger, then they'll get a better reading score on that test. So that's kind of what I mean is it doesn't mean that we have any type of relationship that is maybe influential in the results, but we can't say for sure that it's no cause and effect again.
Okay, that makes
sense.
Okay,
thank you.
Okay, thank you so much for spending these extra couple minutes.
Sure.
I'm sure everyone really enjoyed the presentation. Also, for all of the attendees, Dr. Borror has been generous enough to provide us with a PDF version of her slides, which I will send out to everyone through email within the next couple of days. So that's all the time that we have, but thank you everyone so much for joining us, and thank you again, Dr. Connie, for presenting with us. You're great as always. And
thanks everyone.
Has a great day. Thank you. All right, bye.
Bye.